you for the introduction. So, I really like the first thing, one of the first things you mentioned today on your presentation about the T-shaped competence, and I hope that this talk will sort of widen your T a little bit for all of you who work in UX and design, because I'm going to talk about hypothesis-driven development from a data perspective, going through the different parts you need to know in order to understand hypothesis-driven development as it looks like from the data team's side. So, just starting with what hypothesis-driven development is. It's not something invented by tech companies or anything. It's been around for ages, but used in science. And then for the last decade or two, it's been adopted and slightly altered and used in tech more and more. So it's a method or process that will help you to develop your product in the right direction. And the process consists of three major steps. You can do different divisions of it, but I prefer to see it as 3 steps. So you start by analyzing your users, and then you create a testable hypothesis of what features they need. Then you develop your feature, and you test it. So instead of just shipping the feature, hoping that you had the best idea from the start, you send it out to a subpopulations of your user, and you see if it compares better than your old version of the feature. So in science, this wouldn't be called an A/B test as we do in tech. You would probably call it an experiment. And say that you were a pharmaceutical company and not like APPRL or APPRL or something like that. Then you would, get a lot of lab rats. You would give them a disease, and then you develop a pill that you hope will cure this disease. You will give this pill to half of the rats, and the other half won't get any pills at all, poor things. And then you wait and see if the rats who got the pill were cured or not. And that's how you know if your new pill is working. And hypothesis-driven development is doing the exact same thing, but with your new features or your new products. So after you've done the test, you learn. You learn from the test you ran, like, was this feature successful or not, and why was it? So, in order to create a good hypothesis, I like to use this template. You have 4 bullets, 4 beginning of a sentence, and I'm going to illustrate them with an example here. So, let's say that we were planning on rebuilding our sign-up page. Most companies have a sign-up page. You have some kind of users, and they need to create an account or something. So we've been looking at the product usage data on the sign-up page, and we've learned that based on the insight that we received then, that new users support the sign-up page to return at a later time. So maybe we looked at visit statistics on the sign-up page. We've seen that it has a lot of abandons, and then we also see that some users, based on their cookies, they return at a later point in time and complete the sign-up flow. So we know that they start filling in the sign-up page, but then after a while they drop out just to return at a later time. So we have this insight. So we think that if we save the user's provided information, so we develop a new feature, we'll make the sign-up flow less tedious when retyping information isn't necessary. So we have the new feature we want to develop, and this is the change in user behavior or in user experience that we want to achieve, so that the conversion on the sign-up page will increase with at least 4 percentage points. And this last step here is crucial for working with hypothesis-driven development, because if you only have an idea, you develop a feature and you say, oh yeah, but this is the user behavior we want to change. If you don't have a way of knowing if you reach that change in behavior or experience, then you don't know if your new feature was a success or not. So you really need to have this last step and decide, okay, if we get this change in behavior that we want, how will that manifest itself in our metrics? So, doing a hypothesis like this, one of the trickiest part is the first step, getting the insight. And to get insights, you need data. So the question is, where do we find the data to get good insights? as a data scientist, one of my favorite places is product usage data, which means that you track everything that your users are doing. What buttons are they clicking? How long are they in your product? How often do they use your product? Do they churn? How does the usage pattern look like? And this is really powerful, and if you have a team of analysts who looks at this data, you will learn a lot and get a lot of good ideas for future development. The drawback of it is that it's kind of expensive to set up. If you're a small startup, maybe your first investment won't be hiring a data engineer, data scientist, building a pipeline, having a nice data warehouse in Redshift, and so on. So it's good if you're mature enough to have it, but we need other ways that you can start with right away as a company as well. And we have user research. This is good for both small and big companies. I know we have a lot of user researchers here, and the insights you can get from user research is super valuable. They can tell a different story than you can tell from just looking at usage data. And the best thing is that you can use it even if you're really small, you have a few users and anything, you can use user research. But you can also have it when you're a huge company like Microsoft or Facebook. So going out, looking at your users, how do they actually interact with the product in real life? So if you can have a team of user researchers and a team of analysts looking at the product usage data, you have a really solid foundation for getting good insights in order to formulate good hypotheses. However, both of these are sort of expensive, so I will give you two other options of data sources. One of them is using reports from customer support and sales. Like the user research people, they meet and talk to users on a day-to-day basis. However, when the user researcher has a more holistic view of the user experience and the user journey, the customer support and sales have a more narrow focus. They will try to either sell the product or they will try to just help the customer with the problem they have at hand. Which means that when you listen to customer support, for example, you will probably mostly get ideas for new feature that involves, fixing small friction points or solving bugs and things like that, whereas a user researcher will be able to, see the potential in your product and finding new fields for your product where you can use it. And then last, we have experience or gut feeling. It's not the most solid data point, if you even can call it a data point, but you shouldn't neglect it all in all. I mean, if you have someone with a lot of industry experience, that person is worth listening to, and that person can have really good ideas. Just make sure that you expose them to this framework of hypothesis-driven development. You experiment on the features that you develop based on someone's gut feeling. Because if you do, then please do know that if that person's gut feeling is completely off, you won't ship the bad product because you will tested it before. So, say in our example, we got the insight from looking at product usage data, and we developed this new sign-up page, and it's time to do the second step of the process, creating an A/B test. So most of you know that an A/B test consists of splitting your users in two groups randomly, and you expose each group to one of the two features. So either to the new one or to the old one. And then you compare the chosen evaluation metric between these two groups. So in our case, we chose conversion rate. So then we would see, do we get a better conversion rate for the new feature or for the old one? What's really important when you create an A/B test is that you do the group selection randomly. Because if you do, then the distribution of users in each group will be the same as the distribution of users in your overall user base. You will have the same proportion of old people, the same proportion of young people, the same proportion of each market, and so on. If you would split by room, say by market or by gender or age, then you will have a bias in your experiment, and you will end up doing an experiment, getting a result that feature A performed in one way and feature B performed in another way, but you don't know if that's because of the feature or if that's because of differences in these two groups. So that's why it's really important to do the group selection randomly, because then you know that the only difference between the groups is the feature itself. So, in our example, we got an A/B test result. In the old version, feature A, where we didn't save the information, we got a conversion rate of 52%. In the new feature, we got a conversion rate of 54%, so we got a small improvement. another big question arises, which people tend to fail on interpreting. How sure can we be that the reality is reflected in this result? So, to answer that, we need to go into some statistics. So let's pretend we're running this exact same experiment 1,000 times. Then and then for each experiment, we register what the conversion rate did we get. So we're running the same thing, testing the same features on not the exact same group, but on same group size. And then on the x-axis here, we have the different conversion rates we receive. And on the y-axis, we have the number of experiments ending up with a certain conversion rate. So what would happen if you would do 1,000 experiments like this is that you would get a normal distribution of results. And what does that mean? It means that most of the experiments will end up at a conversion rate with, which has the true conversion rate of your feature. And the true conversion rate of your feature is not something you can know in reality, but here I did just a simulation from a normal distribution, so here I know. And the thing is, when you run an A/B test, your result will be a random sample from a normal distribution with the mean at the true performance of your feature. So this means that you can be, as you can see, I mean, when we run 1,000 experiments, you will be unlucky sometimes for, say, feature A, and in a handful of cases, you will end up with conversion rates of 37%. And in our specific experiment, we ended up with feature B performing slightly worse than its average and ending up on 54%, and feature A performed slightly better than its average and ending up on 52%. So what I'm saying is that even if feature B is better than feature A, you will sometimes get another result. And the frequency of experiments that produces false results like this is determined by the selected significance level and power. So just a quick raise of hands. How many of you have heard about the significance level? How many of you have heard about the statistical power? Not as many, okay. So, significance level is the rate of experiments that will falsely tell you there is a difference between A and B, even though there is no real difference. And typically, there's an industry standard to use 5%. You don't have to do it, and I'll talk more about that soon. So this means that, say that you would run what we call an AA test. You're testing feature A against itself. Then you would expect no difference between the two groups, right? But if you would do an AA test over and over again 1,000 times, and you have significance level 5%, then in 5% of those experiments, you would say, we have a statistically significant difference between these two groups. So feature A is better than feature A. And of course, that's not the case. It just happens to be so by random fluctuations between the two groups you have. Then we have the statistical power. That's the rate of experiments that will correctly tell you when there is a difference between feature A and feature B. So in our example, where we had a difference between feature A and feature B, it means that if we would use a power level of 80%, we would detect that difference in 80% of the experiments we run. And these two parameters are determined by the sample size you use and the minimal detectable effect. So the sample size is simply how many users do you have in each group. And the minimal detectable effect is the smallest change you will be able to detect with the chosen power you have. So if you think that the conversion rate will go from, say, 50%, that could be the historical average, to 54%, then the minimal detectable effect is 4 percentage points. So that's what we had in our hypothesis here, right? We said that doing this new sign-up flow, we think that we will increase the minimal detectable effect with at least 4 percentage points. The horrible thing is that any changes smaller than the MD will be considered insignificant. So remember the result we had here. We had 52% for feature A and 54% for feature B. That means that we will say that there is no significant difference between feature A and feature B. There is a difference, but we can't say that that's not just due to random chance. So you might ask yourself now, like, why didn't we just use a smaller minimal detectable effect? If we would have used 1 percentage point, then we would have detected that difference, right? And as you might suspect, the answer is not that simple. There's a balance act of choosing these parameters. So the significance level, the power, the sample size, and the minimal detectable effect all interact with each other. So decreasing the minimal detectable effect, it will give you either higher significance and lower power levels, which is bad because you will get the wrong result more often, or it requires you to have a bigger sample size. And increasing the sample size will either give you a longer test time, or it won't be possible with your current user base. So in our example of the sign-up page, it will give you a longer test time, because if you want to double the sample size, you would need to run the test for twice as long in order to let more users pass through your sign-up page. And I mean, you can always do that, but you don't want to run an experiment for 6 months, because you want to ship your feature faster than that. And if you're testing something on your existing user base, and say you have 10,000 active users, then you're limited by that. You can't do an experiment with more than 5,000 users in each group. So the math behind calculating sample size and how all these parameters interact is kind of complicated. And if you're not too keen on the maths, there's a really great sample size calculator here, which I double-checked that it computes the correct result. You can just Google Even Miller sample size calculator, and you'll get it there. I can also send out the slides. I see a lot of people taking pictures now, so I guess that they will be sent out somehow. Yeah, great. Finally, we have the art of choosing the evaluation metric. So here we have the conversion rate, right? And I mean, that's not really, I mean, you're not building a product with the goal of having high conversion rates in your product, right? You have another goal. Most of the time you want to generate revenue or profit, like high-level metrics. They're very relevant to your overall goals, but they have an issue, and that is that they move really slowly. Say that we said that, okay, we want to do a new sign-up page, and we say that we think that this will increase our revenue with 2%. Then we would have to wait for these new users to become paying users, and then we would have to wait for a few months for them to generate enough revenue, and it will take like 6 months, 12 months or something like that to evaluate this experiment. So what we do instead is we use low-level metrics like conversion rates, new users, or something like that. And they are proxies of the overall goal, because we imagine that, okay, if we increase the conversion rate, we'll get more new users. If we assume that the average revenue per user is the same, then we will generate more profit. Yay! So the danger here, and they have the advantage, of course, that they can be evaluated immediately after the experiment is run. But the danger is the word assumption. So did you hear that I said, assume that the average revenue per users will be the same? And how do you know that's true? So when you're doing your hypothesis, you need to be really careful that the feature you're developing is not impacting the low-level metric in a good way, but the overall goal in a negative way. So say that we create a new sign-up page. It improves our conversion a lot, but it hurts the average revenue per user. Then we might end up getting a bad result from this feature, even though it looks like a success from the initial A/B test. So what you can do here is to have like a follow-up on all your experiments with low-level metrics. So half a year or 1 year later, you go back, comparing these two groups that you exposed to the experiments, and see how do they perform on the overall level. And you'd be surprised how many times you will have a really nice impact on the low-level metrics and no or negative impact on the high-level ones. This is especially true when you're running campaigns and you try to, reactivate customers by giving them free stuff or something like that. They usually give a huge spike in reactivation rate and number of users, but when you look back at it 6 months later, they have churned again, and all you have is money spent on giving free stuff to users who never really wanted to use your product anyway. So, I've talked about the analyzing stack, where you can find the data and how you should work with product usage data and user research. I've talked a lot about the testing, and then I just want to, before we end, encourage you to, in the learning step here, don't settle with just looking at the A/B test result and learning if was feature A better than feature B or not. Also ask yourself the question why. So say that now feature B wasn't an improvement from feature A. Why was that? go out and talk to the users who were exposed to this page, or analyze the usage data we have from them, and try to find an answer to that question. Because when you do that, when you put your data team and user research team on it, you'll immediately bump up to the first step in the process. You'll be analyzing your users, you'll get new insights, new ideas for new features, and before you know it, you have this process running, and you're working with hypothesis-driven development, and I assure you that that will help you to develop your product in the right direction, which is, of course, what we want to do. So, thank you. If you have any questions afterwards,